Calculus is a branch of mathematics that studies change and motion. It helps us understand how things grow, move, and change over time, such as speed, area, and curves. Historical background of calculus was developed independently in the late 16th by two mathematicians, Isaac Newton and Gottfried Wilhelm Leibniz. They created calculus to solve problems in physics, especially about motion, gravity, and change. Why calculus was created? Before calculus, mathematicians struggled to solve problems involving changing speed like acceleration, finding the slope of curves, measuring irregular shapes. Calculus was invented to handle these problems more accurately.
Have you ever wondered how mathematicians figure out what happens when a value gets really close to something but never actually reaches it? That idea is called a limit, and it's one of the most important concepts in calculus. In a general sense, limit allows us to determine what value a function is approaching. So when we take the limit of a function, we are describing where it's going. Let's see an example of this with the function 3x squared minus 1. For this function, I'm really curious what value the function is approaching as I use x values close to the number 2. Let's see this by using some input like 1.9, 1.99, and 1.999. When I use these, I get values such as 9.83, 10.8803, and 10.98800. From these values, it appears that the function is approaching 11. So we say that the limit of a function as x approaches 2 is 11. Now at this point, you might be thinking, that's fantastic, but couldn't you have found the limit simply by plugging in 2 into the function? Wouldn't that also give you 11? In this instance, the answer is yes. But the focus with the limit should be on what value it's approaching. And there are some functions where we simply can't plug in a number to find the limit. In other words, they are not always the same. Let's see how this works with yet another function. Let's go ahead and use x squared minus 4 all over x minus 2. Like before, we are interested in what value the function approaches as we use x values close to 2. Let's choose some inputs like 1.9, 1.99, and 1.999. When we use these, we get values like 3.9, 3.99, and 3.999. From these, it appears that the function is approaching 4. So again, we say that the limit of the function as x approaches 2 is 4. Now if you try to find this value by instead plugging in 2 into the function, something strange happens. When you plug 2 into the function, you get 0 divided by 0. This shows that the function doesn't actually get to 4. In fact, a quick look into the graph shows a hole right where 4 is. Despite the hole, the behavior of the function leading up to it is the same. Since the behavior is the same, we still say that the limit of the function as x approaches 2 is 4, even though it never actually gets there. That is the key difference with limits. They're used to describe what value the function is approaching, not what value the function actually reaches. I hope both of these examples really highlight how limits focus on the behavior of the function. To wrap things up, a limit reveals what value the function is approaching, focusing on how the function behaves near a number. And most importantly, limits are the very foundation of calculus. So the next time you come across derivatives or integrals, just remember it all starts with limits. I hope this video helped you understand limits. Thank you for watching and see you in the next lesson. Bye!
One-sided limit is a value that a function approaches as the input variable approaches a given point from either the right or the left. The left-hand limit refers to the specific value that a function or an expression approaches as the input variable moves closer and closer to a particular point from the left side, without actually reaching that exact position. The right-hand limit refers to the specific value that a function or expression approaches as the input variable moves progressively closer and closer to a particular point of interest from exclusively the positive side or higher end of the numerical scale. Example, let's take the function f of x equals x squared as x approaches 5. Right-hand limit. we use values slightly larger than 5, like 5.1, 5.01, and 5.001. Putting them together, we get results that get closer and closer to 25. Left-hand limit. We use values slightly smaller than 5, like 4.9, 4.99, and 4.999. Putting them together, the results also approaches 25. Since both sides approaches the same value, the limit exists and is equal to 25.
Hi guys, let's study about asymptotes. Have you ever seen a graph that gets super close to a line but never actually touches it? Well, that's what we call an asymptote. Today, we're going to learn what asymptotes are, the different types, and how to find them easily. What is an asymptote? An asymptote is a line that a graph approaches but never touches. It's like the graph is trying to reach the line but just can't get there. Here are the types of asymptotes. There are three main types of asymptotes. Number 1, vertical asymptote. Happens when the function is undefined at a certain value of x. This actually occurs when the denominator becomes 0. Here the example. F of x equals 2 and x minus 2. The vertical asymptote is at x equals 2 because the denominator becomes 0 there. Number 2, horizontal asymptote. This tells us what happens to the graph as x becomes very large or very small. Here the example. F of x equals 3 over x. As x goes to infinity, f of x approaches 0. So the horizontal asymptote is y equals 0. Number 3, oblique slant asymptote. This happens when the degree of the numerator is exactly 1 higher than the denominator. Here is the example. F of x equals x squared plus 1 over x. Simplify. F of x equals x plus 1 over x. As x gets large, 1 over x becomes very small. So the graph follows the line y equals x. That's the slant asymptote. Here. Why are asymptotes important? Asymptotes help us understand the behavior of graphs, especially near undefined values or at infinity. They make graphing functions much easier. And that's it. Now you know the three types of asymptotes and how to find them. If this helped you, don't forget to like, share, and subscribe for more easy math lesson. Thank you.
Hey guys, welcome back to my channel. Today, we're going to talk about something super important in basic calculus, the limit laws. Don't worry if this sounds scary. I'll break it down step by step so it's easy to understand. By the end of this video, you'll know the limit laws, why they work, and how to actually solve problems using them. Let's go! Before knowing the limit laws, let us first understand what a limit is. A limit tells us what value a function is approaching as x gets closer to a number. Think of it like this. I'm walking towards a door, I'm getting closer and closer. That's what a limit is. For example, if x gets closer to 2, what happens to f of x? That approaching value, or the 2, is the limit. Now instead of solving limits the hard way, We use limit laws to make everything faster and easier. Let's get into them one by one. The first law is the constant law. There's a statement that says the limit of a constant is just a constant. Why? Because a constant doesn't change no matter what x is. So even if x is approaching something, the value stays the same. Here we have an example. The limit of c as x approaches to a is c. Let's have another example. The limit of 5 as x approaches to 2 is just 5. See? Easy, right? Just remember that no matter what x is, 5 is always 5. Now let's go to the second law. The limit of x as it approaches a is just a. Because x is getting closer and closer to a, so naturally its value becomes a. We have an example. The limit of x as x approaches to a is just a. Let's have another example. The limit of x as x approaches to 3 is just 3. Next, we have the sum law. The limit of a sum is the sum of the limits. As each function approaches its value, you can just add those results together. So for this law, we need to apply the operation addition. For example, the limit of f of x plus g of x as x approaches to a is equals the limit of f of x as x approaches to a plus the limit of g of x as x approaches to a. Let's have another one.
The limit of x plus 3 as x approaches to 2 will equals the limit of x plus the limit of 3. Now, the limit of x is 2, so just simply substitute. 2 plus the limit of 3 is equals 5.
Fourth, we have difference law. The limit of a difference is the difference of the limit. Same logic as addition. Approach each value first, then subtract. This is just similar to the sum law. Let's have an example. The limit of f of x minus g of x as x approaches to a is equals the limit of f of x as x approaches to a minus the limit of g of x as x approaches to a. So in this law, we need to apply subtraction. What we're going to do is we're going to subtract. Let's have the limit of x plus 1 as x approaches to 4 is equals the limit of x is 4 minus the limit of 1 is equals to 3. Next, we have the product law. The limit of a product is the product of the limits. If both functions are settling into values, multiplying those final values will give the result. So for this law, we are going to apply multiplication. Now, the limit of c times f of x as x approaches to a is equals c times the limit of f of x as x approaches to a. Let's have the limit of x times 3 as x approaches to 2 is equals the limit of x is 2 times the limit of 3. We have 6. Next, we have the constant multiple law. In this law, you can factor out constants. Why? A constant doesn't depend on x, so you can just pull it out and focus on the function. For constant multiple law, we have the example, the limit of f of x times g of x as x approaches to a is equals the limit of f of x as x approaches to a times the limit of g of x as x approaches to a. Let's have the limit of 5x as x approaches to 2. Now, pull out this constant, so it's just gonna be the limit of 5 times the limit of 2 equals to 10. Next one, we have the quotient law. The limit of a quotient is equal to the quotient of the limits, as long as the denominator is not equal to 0. As long as the bottom isn't 0, division behaves normally. Let's have its example equation. The limit of f of x over g of x as x approaches to a is equals the limit of f of x as x approaches to a over the limit of g of x as x approaches to a, and the limit of g of x as x approaches to a must not be equal to 0. So, let's have the limit of x over 2 as x approaches to 4 is equals, our x is 4, so 4 over 2. Now, 4 divided by 2 is 2. Our answer is not equal to 0. Correct. So for the next one, we have the power law. If a function approaches a value, its power approaches that value raised to the power. So first you need to take the limits, then apply the exponent. We have this example equation. The limit of f of x as x approaches to a raised to the power of n is equals the limit of f of x as x approaches to a raised to the power of n. Have the limit of x squared as x approaches to 3. So x approaches to a is equals 3 raised to the power of n, and our n is 2. So 3 times 3 is 9. That's your final answer. So that's it for power law. Now let's have the root law. Roots are just another operations like power, so we apply it after finding the limits. Here let's have an example. The limit of square root of x as x approaches to 4 is equals the square root of 4. The square root of 4 is 2. Here's your answer. Root law is easy, right? Now let's head to the last law, the substitution law. Substitution law for me is the easiest law if the function is continuous. If the function is continuous, just substitute the value. For nice functions like polynomials, there are no breaks, so you can just directly plug in the number. So for substitution law, we have the equation. The limit of f of x as x approaches to a is equal to the limit of f of a. The limit of x squared plus 3x as x approaches to 2. So what we're going to do first is we're going to substitute 2 into the x. Let's have 2 squared plus 3 times 2. Now, 2 times 2 is 4 plus 3 times 2 is, that's right, 6. Now, we're going to add 4 plus 6 equals 10. And 10 is your final answer. And that's it, guys. Those are the 10 limit laws made simple. If you remember one thing, yes, limit lets you plug in values as long as the functions behave nicely. If this helped you, don't forget to like, share, and subscribe for more math tutorials made easy. Thanks for watching!
Calculating limits is the process of determining this approaching value using algebraic and analytical techniques. In many basic cases, this involves direct substitution. Substitute the value of x into the function. If everything behaves nicely, no drama, the limit is simply the function's value. Indeterminate forms. If substitution results in expressions like O to O or infinity to infinity, don't panic. This is calculus saying look closer. Algebraic simplification. Using factoring, canceling, or rationalizing to clean up the expression and reveal what's really going on behind the scenes. Reevaluation. Try substituting again after simplification to find the actual limit. Limits are closely related to continuity, where a function is continuous if the limit equals to the function's value at the point of basically no sudden jumps or plot twists. They also form the foundation of derivatives, how things change, and integrals, how things add up, making limits the quiet overachievers of calculus. Sometimes, we also consider one-sided limits, looking at values as x approaches from the left, x to negative a, or to the right, x to positive a. If both sides agree, the limits exist. If not, well, even functions can be indecisive. In short, calculating limits helps us understand how functions behave near specific points. Even when direct answers aren't immediately available, it's all about getting closer and closer to the truth, one step at a time.
We've been talking about how graph moves smoothly, flowing without any interruption. But sometimes the graph breaks. It may stop suddenly, jump to another place, or even shoot off to infinity. There's three types of discontinuity. The first one is the removable. Everything's look normal except for the one missing points like tiny hole in the graph. The second is the jump. The left and right side don't connect, like step instead of a smooth path. The third one is the infinity. The graph goes up or down forever and never comes back. Now, let's look at this function. F of x is x squared minus 4 over x minus 2. X approach 2. We're going back to what we learned about limits. We first try direct substitution. If we substitute 2, we get 0 over 0, which is undefined. So we simplify by factoring. So equals x plus 2 parenthesis again x minus 2 over x minus 2. So we're gonna cancel out these two, or the x minus 2. The numerator is become the x plus 2. So now we just substitute again. 2 plus 2 equals 4. So where did I get this? Well, the x is 2. So I put 2 here. So the answer is 4. So the limit is 4. But just like that before, the original function is still as a whole at the point 2 and 4. This means we have a removable discontinuity. To fix this, well, tell the graph what value it should have when x is exactly 2. We do this by writing it as a piecewise function. F of x equals x squared minus 4 over x minus 2 for if x equals 2. And just like that, we fill the hole and make the graph continuous again.
Good day everyone! Today I will going to discuss what a derivative is and how it solve it and how it help us in our real life situation. First, what a derivative is. A derivative is a concept in calculus that tells us the rate of change of a function. In simple terms, it shows how fast something is increasing or decreasing. It also represents the slope of a curve at any point. For example, if you are driving a car, the derivative of your position tells your speed. So, derivatives are very useful in science, engineering, and everyday life. And of course, we have a rule in solving. To solve the derivatives easily, we use the power rule. I'm gonna show you the rule of solving. This is the rule of solving. This means multiply the coefficient and exponent. Subtract 1 from the exponent. This is the example problem. Find the derivative of f of x is equal to 2x squared plus 3x squared minus 5x. In this example, we use step-by-step solution. Step 1. Differentiate each term. And for 2x squared 3, 2 times 3 is equals to 6. Exponent becomes 3 minus 1 is equals to 2. Result 6x squared and 2. And for 3x squared and 2, 3 times 2 is equals to 6. Exponents becomes 2 minus 1 is equals to 1. The result is 6x. And for negative 5x, negative 5 times 1 is equals to negative 5. The exponents become 1 minus 1 is equals to 0. The result is negative 5. In the step 2, combine all the result. F of x is equals to x squared 2 plus 6x minus 5. Final answer. The derivative of 2x squared 3 plus 3x squared 2 minus 5x is 6x squared plus 6x minus 5. How derivative helps to solve the problem. Derivatives are useful because they help us to find the speed or velocity of an object, determine the maximum or minimum values like profit or cost, understand how quantities change over time. For example, businesses use derivatives to find the best price to maximize profit, while engineers use them to design safe structure. And that's all. Thank you for watching. I hope you learned something about derivatives. Subscribe my channel.
時間は有限短いウィーケンありきたりな